Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session of mechanical properties of solids, where we discussed the basics of elasticity, what is stress, what is strain, and the Young's modulus of elasticity, and we solved some questions related to that, and what are the different types of stress and different types of strain, and we solved some questions related to that. So, and in continuation of the same chapter, that is mechanical properties of solids, today we are going to discuss the lecture number 2. So where in the lecture number 2 we are going to focus on the bulk modulus of elasticity, so which is an important topic, and then the stress strain curve, where the theory questions can be directly picked from here for any competitive examination. So whether it's NEET or JEE or BITSAT or WB-JEE or MSET or whatever it is, KSET, so whatever the exam that you are appearing, so the questions can be directly picked from here, okay? And we'll also see what is the Poisson's ratio in today's session. So as usual guys, I just need your attention for the next 1 hour. So just be with me, avoid all the disturbances around you, and at the end of the lecture, it's very important to prepare your own short notes. Done? Chalo. So let's begin the today's session with very high positive energy and with the question. So let's try to solve this question on your own. So first try to read the given question properly and understand the given information. So if the ratio of diameters, lengths and Young's modulus of steel and copper wires shown in the figure are P, Q, S respectively, so then the corresponding ratio of their increase in their lengths, see here. So what is, see at the end of the question, then the corresponding ratio of their increase in lengths. So increase in lengths means elongations ratio. So elongation in the case of steel to the elongation in the case of copper, so is equals to how much? So this is equals to how much? That's what they are asking. So I can write, so first write the given information. So what's the given information? So the diameters ratio, so the ds to that of d copper, so that means diameter of the steel to the diameter of copper is equals to P. And what else they gave? So length, so the length of steel to that of the length of copper is equals to Q. And then the length of the next Young's modulus of steel to that of Young's modulus of copper is equals to S, right? So this is the given information. So you already know the formula. What's the formula for Young's modulus of elasticity? So Y is equals to FL by A into delta L. So actually we need the delta L formula here. So the delta L is equals to FL by AY, FL by AY, right? So now, so I can write what is DS by DC ratio I know, and LS by LC ratio I know, YS by YC ratio I know. Here the force ratios also let's find. So this is the steel wire and this is the copper wire. Hope you are able to see this one. This is steel wire and this is copper wire. So copper wire is having a weight of 5 m, so that mass attached to the copper wire is 5 m. So that's why the weight will be 5 mg. So I can write, so for the copper, the load on the copper wire is 5 mg. Yes or no? But for the steel wire, so this mass and this mass both are attached. So that's why I can write, so the weight or the load attached to the steel wire is, so 2m plus 5m, it is 7 mg. So this is the force. Now let's write the formula. So what we can write here? So do we have this template here? If it is there, we'll choose no. So just let's go for the normal template. Chalo. So then I have got, so the delta L is equals to FL by AY, FL by AY. So now I need delta LS to the delta copper. So which is force, the first delta LS, force of steel and L of steel and area of steel and then Young's modulus of steel by, so force copper and L copper by area copper and then Young's modulus copper. So let's write the formula first. So I can write it as FSLS by ASYS into, so here we can write this as ACYC by, so FCLC. Done. Chalo. So let's write the terms aside. So I am writing FS by FC aside. Let's write this part, and then let's write LS by LC aside, and then so I am writing so YC by YS, just write aside, and then AC by AS. So let's write this way. So then I can write here, so the force of the steel wire to the copper wire. So steel wire 7 mg, copper wire 5 mg. So I am writing 7 mg by 5 mg steel to the top of the copper, and then so LS by LC, so LS by LC, which is Q, so which is Q I am writing, and then next we have YC by YS. So what is YC by YS? So YS by YC is S, so YC by YS will be 1 by S, so this is 1 by S, and then so let's write areas. So let's do one thing. So they gave the diameters ratio, right? So let's write the area will be pi d by 2 whole square of the, see here, copper by, so pi d by 2 of the steel, copper to the steel, right, whole square. So I can cancel pi pi, and then so here 4 also will get cancelled. So let's write this way. So mg cancel, 7 by 5, and then Q by S. So here what is left? See here. So DC square by DS square, right? So here 4 also gets cancelled. So I can write here 7 by 5 into Q by S into, so what is DS by DC by DS whole square? We have got DS by DC is given P. So DC by DS will be 1 by P. So this will be 1 by P whole square 5S. So 1 by P whole square means 1 by P square. So the final answer will be 7Q by 5P square S. 7Q by 5P square S. So 5Q no. 7Q by 5P square S. Option 2. This is 7Q. So this is 2Q here. Okay, so this is 7Q. So this is 5 SP only, here 5 SP square. So we have got SP square, right? Yes. So this is how you should do these kind of questions. Done, guys? Chalo, good. So let's move for the next question. So let's see the second question. What's the question says? First read the question. I'll just stand aside. First read the question. So copper of fixed volume V is drawn into wire of length L. Okay. So when this wire is subjected to a constant force F, so the extension produced in the wire is delta L. So which of the following is a straight line? Okay. So see here. Which of the following graphs is a straight line? So which of the following options may be correct? Okay. So that's the question says. Okay. See here. This is a wire which is of initial length, how much? Length L. So now it is subjected to a constant force F. It is subjected to a constant force F, so that so it is elongated by the length delta L, right? So the delta L. So now the delta L is proportional to what? So that's what they are asking. So first thing is the delta L is directly formula. What's the formula? FL by AY. FL by AY. So but the thing is here we have to check only with the L. So most of the students they directly write delta L is equals to L. Delta L is directly proportional to L. So where is that option? So option 4. But that is absolutely wrong. See here. So copper of fixed volume here. So we don't have any term related to volume. Yes. So if this copper has cross-sectional area A, so its volume will become, shall I say, the cross-sectional area into the length, the cross-sectional area into the length, right? So in place of this area, shall I write volume upon length? Volume upon length. So that FL by A, in place of A, I am writing volume upon length into Y. So this L will go up, FL square by Vy. So FL square by Vy. So here, so the delta L is directly proportional to L square here. So this is the graph. So the delta L versus L square. Clear guys? Understood? Chalo. Good. So next, so we have one more question. A uniform rod of mass M and length L and area of cross section A and Young's modulus Y hangs from the ceiling. So its elongation under its own weight will be. Okay, fine. So what they are asking again here? So this is a uniform rod of mass M and length L. So this is a rod which is of mass M. So this is a rod of mass M and length L. So fine. So area of cross section A. Good. So and Young's modulus Y hangs from the ceiling. Its elongation under its own weight. See. So if it is just a wire, we just take its weight as total mg downward. But here its own weight, it's a uniform rod of mass M and length L. So its weight acts at the center of mass. So its weight acts at the center of mass. At what distance? At a distance L by 2. So its center of mass will act. So its elongation they are asking. So what's the formula for elongation we have? So FL by AY. FL by AY. So generally in place of this L, so the weight, the force is nothing but its own weight mg. So this weight is acting at a distance L by 2, right? At center of mass it acts. So that's why L by 2 by AY. So the final answer will become mgl by 2 AY. Okay, clear? So mgl by 2 AY. Option 2 is the correct one. Most of the students pick option 3, mgl by directly AY. Okay, so the weight acts at its center of mass. Done? Clear? Chalo, good guys. Next, so let's go for the bulk modulus of elasticity. So first, what's the formula for bulk modulus of elasticity? We discussed it in the last session. So it's a volumetric stress by volumetric strain. It's a volumetric stress by volumetric strain. Volumetric strain. Right? Chalo. So what is a volumetric stress? So what is a volumetric stress and what is a volumetric strain? So strain comes when there is dimension change. So the stress is nothing but force upon area. So here some force is acting upon, so its cross sectional area. So let's write F by A. So the force upon area by, so what is a volumetric strain? So if it is placed in the liquid, so this bulk modulus of elasticity only for the liquid guys, not only for the liquid. If it is the liquid, only bulk modulus of elasticity will be there for the liquids. So here I can write, so as its initial volume is V, its final volume is V naught. So the change in the volume is delta V, right? So the change in the volume delta V by, so the original volume V naught. So the original volume V, let's write. So or else let's write original volume V naught, and then so this is V, final volume V. So then, so this is V naught, delta V by V naught. So as this volume gets decreases, so what's the volume? The delta V is nothing but final volume minus initial volume. So the final volume is less and initial volume is more. So obviously this term will come out to be more because V is less and then V naught is more. Understanding? So this value comes out to be, so minus. So this is 1. So then I can write here, so this force upon area, so the force upon this perpendicular area, so which is nothing but the pressure. So I can write here, so the pressure upon, so minus delta V by V naught. So this is a bulk modulus of elasticity. This is a bulk modulus of elasticity. So you can write it in So this way also. So the bulk modulus of elasticity is, so the change in pressure delta P by, so minus delta V by V naught. So you can write this way also, or else you can also write this as, so the bulk modulus of elasticity is delta P by, so minus dV by dV by V. So this way also you can write. Okay, it's up to you. And one more thing, it will have the same units as of the, so the bulk modulus of elasticity, it will have same units as of the pressure. So B as same units as of pressure. Why? Because the strain will not have any units, right? The volume by volume, so the units gets cancelled, only force upon area. Or we can also say the bulk modulus will have the same units as of the stress. Okay, so what are the units now? So the Newton per meter square, Newton per meter square, or which is also called the Pascal. Did you guys remember from the 9th grade? So the Pascal is the unit of pressure. Okay, so the unit conversions also you should remember. So you already know. So 1 atm is equals to, so we can write 1.01 into 10 to the power 5 Newton per meter square, which is also approximately equals to 10 to the power 5 Newton per meter square. So which is also equals to 1 bar, which is also equals to 760 mm of Hg. So we'll discuss about it in detail in the next chapter, that is mechanical properties of fluids. Okay, as of now you should remember these conversions. And then, so this is the bulk modulus of elasticity formula. Done guys? Any doubt here? Chalo. So let's go for the next. So what is the compressibility? Compressibility is denoted by C. It is simply inverse of the bulk modulus of elasticity. That's it. You can remember this. So the reciprocal of the bulk modulus of the, so the reciprocal of the bulk modulus of the material of a body is called the compressibility of that material. Just remember this one. Okay, chalo. So we have got the question. So let's try this question on your own, guys. Let's try this question on your own. How much should the pressure on a 1 liter of water be changed to compress it by, so 0.10%? That means, so minus delta V by V is given, so we have to compress it, so which is 0.10%. Okay, so and then, so what else they gave? The bulk modulus is, the bulk modulus that they gave 2.2 into 10 to the power 9 pascals. So we have got the formula. So B is equals to, so what we need, how much should the pressure on a, so that is the change in pressure or pressure by minus delta V by V. So what we need from here? So we need the delta P, the change in pressure or the pressure applied. So which is B into, so minus delta V by V. So okay, so which is the delta P is equals to, so B, so which is 2.2 into 10 to the power 9. So 2.2 into 10 to the power 9 into, so what is the percentage? So which is 0.10 by 100, 0.10 by 100. So now you guys can do the calculations. How much you are getting? Just do the calculations on your own fast. Just do the calculations first. So what's the final answer? Done? Chalo. See, simply convert it to percentage. Done? Do the basic calculations, no? So this is 1 by 10 you can write, so which is nothing but 2.2 into 10 to the power 9 into this is 1 by 1000 you can write. So that means 0.10 means 0.1 by 100. So that point, if you take it out, so 1 by 10, so 10 into 100 is 1000. So send this to upside. So 2.2 into 10 to the power 9 into 10 to the power 3. So which is nothing, 10 to the power minus 3. So which is 2.2 into 10 to the power 6 pascals. Simple calculations. 2.2 into 10 to the power 6 pascals. Option 3 is the correct one. Done, guys? Yes, good. So we have got one more question. So what's the question says? So to what depth below the surface of sea should a rubber ball be taken as to decrease its volume? So decrease its volume, minus delta V by V is given. How much? So 0.1%. Fine. So take density of sea water as 1000 kg per meter cube. So 10 to the power 3 kg per meter cube. So and the bulk modulus of rubber 9 into 10 to the power 8 Newton per meter square. So what we need to find here? So to what depth below the surface of the sea? So let's consider this is the surface of the sea. Now, so to what depth you should take the rubber ball so that its volume decreases by 0.1%. See, you know that as you go down, the pressure increases. So that we'll study it in the next mechanical properties of fluids. So here the atmospheric pressure P0 will be there. So if you go inside the liquid, the pressure increases. Let the pressure here be P. So now the final pressure will be equals to P0 plus rho GH. So hope you guys already have this idea in your grade 9th itself, right? So now the change in pressure P minus P0 is equals to rho GH. P minus P0 is equals to rho GH. So P minus P0 means the change in pressure, which is rho GH. Yes. Now, so I am going to use the same formula. We have the bulk modulus of elasticity is equals to the change in pressure minus delta V by V. That's it. So now what is the change in pressure? So the change in pressure, in place of that I can write rho GH, because I need to find what is the depth. H I should find. So from the pressure formula, how I relate it to the depth, so that's the concept here. Okay, so rho GH minus delta V by V. So simply substitute now. So it's easy now, you guys can solve it easily. So B is equals to, so rho is 10 to the power 3 density of water into H G 10. H I have to calculate by, so this is 0.1%, which is nothing but 0.1 by 100. So then B is equals to, you can write 1 by 1000, 1 by 1000. So that 1000 also will go up. So that means 10 to the power 3 into 10 to the power 3 into 10 into H. So what is the B value that they gave in the question? So 9 into 10 to the power 8 is equals to, so 6 plus 1, 7. So into H, right? So then H is equals to, here 8 and 7 gets cancelled. So we have got H is equals to 110 will be left. So 9 into 10. So H is equals to, so 90 meters is the correct answer. So H is equals to 90 meters. Option 4 is the correct one. Clear, guys? Everyone? Done? Chal. So let's move further. So try this question on your own. So try this question on your own, everyone. First. Same concept, same previous concept, that's it. The approximate depth of an ocean is 2700 meters. The compressibility of the water is given. Compressibility means the bulk modulus will be 1 by compressibility. Okay. So and the density of the water, not 103, it's a 10 to the power minus 10 to the power 3, guys. 10 to the power 3 kg per meter cube. So then what fractional compression of water be obtained at the bottom of the ocean? What fractional compression? So fractional compression means the change in the volume to the original volume. So this is what they are asking. So the simple thing, so I know the formula, B is equals to delta P by minus delta V by V naught. Yes, I have to calculate this value. Fine. Chalo. So then I can write in place of bulk modulus 1 by compressibility. Yes. So the change in pressure is rho GH by, so this is minus delta V by, so V naught, that's it. So now I need this one. So 1 by compressibility is what? What is compressibility they gave? 45.4 into 10 to the power minus 11. Done. Shall. So which is equals to rho. So what's the density? 10 to the power 3 into G 10. So and then height, so 2700. Yes, by, so this is delta V by V naught. So then I can send this to, so do the cross multiplication here. So simply do the cross multiplication. So then we can write delta V by V naught. So you can put minus also, no issue, because compression means it will come out to be, so the negative of that only. So which is, so 10 to the power 3, 10 to the power 1, so which is 10 to the power 4, so 10 to the power 6 into 27 into, so I can send this to this side, so 45.4 into 10 to the power minus 11. So this is the final answer, so you can calculate it from here. So 27 into 45.4 into, so 10 to the power minus 5. So the options are in 10 to the power minus 2. So let's do one thing. So you multiply these two. So what's the 27 into 45.4? So 27 into 45, so 0.4. So or else let's directly calculate this one. So let's do first 27 into 45. So how much? So 35, 10, 13, so 28, 8, 10. So 5, 13, so 5, 11, 2, 1. So 1 to 1 pi, approximately 1 point. So 3 zeros, if I write it this side, I'll get somewhere around, so 1.2 and 0.4 is also there, right? So I can write somewhere around 1.4. The answer will be somewhere around, so 1.4 into 10 to the power minus 2, because here minus 5 is there, we are getting, so 1215, so like that we are getting. So and 0.4 I did not take. So if I multiply the 0.4, so it will come greater than 1.2 only. So that's why the only option I have greater than 1.2 is 1.4. So I can choose option 4 is the correct one, guys. Okay now. So always do the approximate calculations when the options are bit far. Okay, done. Chalo. Next. Clear? Chalo. Correct only na? Or somewhat less we are getting. So why to have the confusion? Let's do between these two. So let's do the calculations into 27, right? Yes. So let's do the calculations. So 28, 35, 37. So options are closed, right? That's why I'm doing. So 28, so 35, 37. So 28, 31. So then 8, so 10, 8, 9. So then I can get 8, so 15, so 2, 12. So 1, 2, 2, so 5, 8. So I can write 1, 2, 2, 5, 8 into 10 to the power minus 5. So which can, so 3 zeros if you can send it to this side. So 3 points you can send it to this side. So I can put point somewhere around here. So if 3 points if I can keep to this side, so it will become 1.2 into 10 to the power minus 5. So 1.2 only, not 1.4. Okay, so that's why do the calculations, guys, because here the options are closed. If the options are not closed, you can go for the approximation method. Here the options given are closed. Okay, done. Sure. So next, so we have the question number 7. So let's try this question, guys. So the bulk modulus of a spherical object is B if it is subjected to uniform pressure P. So the fractional decrease in radius, see here. So this is a sphere. So it is subjected to, so uniform pressure. So from all the sides, so its uniform pressure is applied. Okay, so then it will be compressed, obviously. Yes. So now what is the fractional decrease in radius? So I know the formula in the bulk modulus is equals to delta P by, so minus delta V, or else let's write simply, however volume is decreasing, right? So let's write delta V by V. So take the magnitude. Okay. So then, so I need what is the fractional decrease in the volume, fractional decrease in the radius. So let's do one thing. So I can write the bulk modulus, the pressure applied is P, right? So P into, so delta V by V. So delta V by V. So chal. So let's do one thing. See, its volume is actually 4 by 3 pi r cube. Now, so if I write, so delta V by V is nothing but, so 3 into delta R by R. So delta V by V is equals to 3 into delta R by R. So they are asking what is the fractional decrease in radius, delta R by R they are asking. So in place of delta V by V, so I can write delta V by V, so I can write 3 into delta R by R, 3 into delta R by R. So send this delta R by R and P to B to this side. So delta R by R is equals to P by 3B. So P by 3B. So P by, so all the options are given same. So change any one of the option to, so this is 3B, this is 2B, this is 4B, so this is B. So write like that. So I can choose the option 4. Here the DTP error is there, so just ignore that, guys. Done? Everyone clear? Chal. Next. So the concept is simple. So now, what is the relation between density, pressure and bulk modulus B? So whenever you apply the force, so the volume will decreases, the volume gets decreases. So the density is equals to mass upon volume. Okay. So when an object is subjected to some force, then its volume decreases. But mass remains constant. So if the mass remains constant in this case, so mass is constant, volume is getting decreasing, so that the density of the material should increase. So mass is constant, volume is getting decreased, so the density should increase. Volume decreases, the density increases. So that the density increases, I can write, so that the density increases. Okay. So then the new density, so the rho dash is a new density which is equals to rho into 1 plus P by B. So where P is the pressure and B is the bulk modulus. So here I am writing, so the rho dash is a new density, and then so rho is the original density, and then so the P is the pressure and B is the bulk modulus of elasticity. B is a bulk modulus of elasticity. So B is a bulk modulus of elasticity. So this is the concept, guys. Done? Everyone clear with this? Chalo. So just note it down. I'll get the remote. First, so note this down. Done, guys? See here, if you want, you can write delta P also, no issue. P or delta P, the change in the pressure. So next, so let's move further. So the density of a metal at a normal pressure is rho. Its density when it is subjected to an excess pressure P, so this is the excess pressure P, is rho dash. So if the bulk modulus of the metal is B, then the ratio of rho dash to the rho. See here. So we know the new density is equals to rho into 1 plus delta P by B. Yes. So they are asking what is rho dash by rho. So rho dash by rho is equals to 1 plus delta P by B, or you can also write it as 1 plus in place of pressure P by B. So check the options, B by rho, B by rho. So this is 1 plus P by B. This is P, guys. So this is P by B. Option 4 is the correct one. Rho dash by rho is equals to 1 plus P by B. Done? Sure. So now let's go for the bulk modulus of rigidity. See, so the bulk modulus of rigidity, which is denoted with, so the neta, so I can write the bulk modulus of rigidity is, so it's a shearing stress by shearing strain. It's a shearing stress by the shearing strain. Shearing stress by shearing strain. So what's the shearing stress here? So let's suppose you applied some tangential force Ft upon, so this area, cross sectional area, you applied the force, tangential force Ft. So that tangential force, let Ft is equals to F we are taking. So that force upon area by, so the shearing strain, we already know the shearing strain, which is equals to the change in the length by the original length, let it be L. So x by L, so which we can also write it as, so as theta is given, the tan theta, right? So here I can write x by L, so which I can write it as, so FL by AX, FL by AX. So this is the bulk modulus of rigidity. So this is the bulk modulus of rigidity. Done here? Clear? So but most of the cases, so this theta is going to be very, very small. The theta will be very, very small. The theta is going to be very, very small. So if the theta is very, very small, so the tan theta tends to almost theta. So the tan theta tends to almost theta. So that means in place of x by L, so we can write theta. So in place of L by x, so we can write theta. So here, so in place of x by L, you can almost write theta. So the other form, I can write this as, so I'll write it with the other color. So which is equals to F by A by, so here x by L almost tends to theta by theta. So which we can also write it as F by A theta. F by A theta. Clear? So this also can be correct sometimes. So when theta is very, very small. Done? Clear? This is the bulk modulus of rigidity. Till now we have seen, so the Young's modulus of elasticity, and then so the bulk modulus of elasticity and the bulk modulus of rigidity, right? Longitudinal stress by longitudinal strain is the Young's modulus of elasticity, and then so the volumetric stress by volumetric strain, so the bulk modulus of elasticity, and the bulk modulus of rigidity, so shearing stress by shearing strain. Done, guys? Chalo. So one important point, that is a solid will have all the three modulus of elasticity. So Young's modulus, bulk modulus and shear modulus of elasticity. So and then, so in case of liquid or a gas, only B. So only B means in case of liquid or gas, only bulk modulus of elasticity. Only bulk modulus of elasticity. So bulk modulus of elasticity. Done? Clear everyone? So good. Let's move further. So let's try this question, guys. A rectangular block of size 10 centimeters, 8 centimeters, 5 centimeters is kept in three different positions P, Q, R in turn as shown in the figure. So in each case the shaded area is rigidly fixed. So the shaded area will be the bottom area you can take. So here it is not shaded actually. So the bottom area. So for this one the bottom area, for this one the bottom area, and for this one the bottom area. Okay. and a definite force F is applied tangentially to the opposite side. So here on the top, see, let's imagine a cube, a rectangular, not a cube, a rectangular block like this. So the bottom one is, the bottom face is there, na? So it is rigidly fixed, the bottom face, and on the top face you are applying the force. Okay, so then tangentially, how the force is applied? Tangentially to the opposite face to deform the block. So the displacement of the upper face will be same in all three cases: maximum in P position, maximum in Q position, maximum in R position. So the displacement X they are talking about. So here, so the force is applied tangentially. First, what kind of modulus of elasticity exists? So the neta, I can say, so I can write, so the neta is equals to FL by AX, FL by AX, yes or no? So then they are asking what is X. So the displacement is more for which one? So F is equals to, X is equals to FL by A into neta. So FL by A into neta. So see here, so F is applied tangentially to the opposite face to deform the block. So the same force is applied in all the cases. So a definite force F is applied. F is same for all. F is same, and then so they all have the rigidity. See here, so the shaded area is rigidly fixed. So you are not changing the shaded area. So this is fixed. So that the neta is also be same for all. Then so that means the displacement, so now it is directly proportional to force is same and neta is same. So it is directly proportional to length and inversely proportional to area. So in each case you find the, so now in each case you can find the F by L ratio. So in the first case, see here, in the first case, so L by, what is that? L by A ratio, right? We need L by A ratio, yeah. So here in the first case the length is 5 by, so the area is breadth, so these two, 10 into 8 in the first case, in the P position. So in the Q position the length is 10 by, so 5 into 8. So then this one 8, so the length is 8 by 5 into 10. So this comes out to be, so how much? 5 by 80. So 5 by 80, yes. So then 5 ones are 5. So let's write that 5 by 80. So let it be. So then 10 by 40, this one done. Chalo. So this one 8 by 50. So which I can write it as 1 by 4. This is 0.25. So this value is fine. So and then this is 1 by, so 16. 1 by 16 means, so I can write, so 0 point something like, I should put one more 0. So then 100. So 0.0 16 6 are right. So 0.06 something like that we get. So here it is 4. So 2 4s are 2 25s are, yes. So then, so here 4 by 25 means, so I can write, so 25 0 point, so if I place 40, yes or no, so 0.40, so which is one time it will go 0.1. So 0.06, 0.1 something you will get. This is 0.25. So for which one the X is more, the L by A ratio, for whichever the one the L by A ratio is more, so then the X will be more. So I could see that here, so it is more for the Q position. So that's why, so the displacement of the upper face will be maximum in Q position. Option 3 is the correct one. Okay, so just the basic concept. Done guys. Chal. Good. So now what is the potential energy stored in stretched wire? So whenever a wire is stretched, see this is a wire. So whenever you apply some force, okay, so then some work is done. If force is applied, so then shall we say some work is done. So the work is done. So whenever the work is done, so the potential energy will be stored in it. If there is a work done, so then the change work done will be equals to the change in potential, the potential energy will be stored, right? So we can write, so that potential energy stored, U is equals to the potential energy stored in the stretched or compressed wire. So let me write. So the potential energy stores in a stretched or compressed wire. In a stretched or compressed wire. So the U is equals to half into stress into strain into volume. So half into stress into strain into, so the volume. So this is the main formula you should remember, guys. So this is a main formula, so that you should remember. So half into stress into strain into the volume. So here you can modify it in different ways. So which is equals to half into, so in place of stress you can write, so the Young's modulus of elasticity, Y is equals to stress by strain, the longitudinal stress by the longitudinal strain. So in place of stress you can write, so gamma into strain. In place of stress we can write gamma into strain. So in place of stress I am writing gamma into, here strain will come, strain into strain, so strain square, right? So into, so the volume, into, so the volume. So this is also one formula. Or else, so you can also write it as, so the potential energy stored is equals to half into stress into strain into volume. Again I am writing that formula. So let's write in terms of the force and length, half into, so the stress is nothing but the force upon area. Let's suppose on this wire you are applying the force F, so that the original length L, so upon cross sectional area you are applying, so that the change in the length is delta L, let's suppose. So then I can write, so half into stress, force upon area, strain is the delta L by L, so the volume is nothing but original cross sectional area into length will give the volume. So the original cross sectional area into the length will give the volume. So L cancel, A cancel. So we can also write it as half into force into delta L, which is nothing but, so the force is nothing but the load, whether it's weight or some other force. Okay, so this is half into, we can write it as load into, so the delta L is nothing but elongation. So delta L is nothing but elongation, that's it. So this is a concept. So this is a potential energy stored in a stretched or compressed wire. In a stretched or compressed wire. Done everyone? Chalo. So a wire is suspended vertically from one of its ends, is stretched by attaching a weight of 200 newtons to the lower end. So see here, first try to understand the given question. So this is a fixed support. So a wire is suspended vertically from one of its ends, stretched by attaching a weight, so 200 newtons. This is a wire of cross sectional area. So now 200 newtons, this is a load, force. So to the lower end, the weight stretches the wire by 1 mm. So now the weight stretches the wire by, so 1 mm. So that means the change in the length delta L is 1 mm. So then they are asking what is the energy stored. So directly I will write in terms of load and elongation. I know the formula, half into load into elongation, the potential energy stored, half into load into elongation. Here I got the formula, I got the value of load. What is the load value? 200. And what is the elongation? 1 mm. So 1 into 10 to the power minus 3, right? So this comes out to be, so 100 into 10 to the power minus 3, so which is nothing but 10 to the power minus 1, which is 0.1 joules. So which is 0.1 joules. Option 1 is the correct one. Done guys, clear? Chalo. So next we have one more question, see here. So what's the question says? So when a block of mass m is suspended by a long wire of length L, the length of the wire becomes L plus delta L plus L. So this is a rigid support. So this is a mass originally. So this is of mass M and length L. So now, so suspended by a long wire of length L, the length of the wire becomes L plus L. So now the length of the wire will become, so L plus L. So that means the elongation is small l here. So the elongation from here to here, so the small l. So then the elastic potential energy stored in extended wire is, so the elastic potential energy is nothing but U. So again the same thing I'll write. So on this one, due to its own weight, it's elongated, right, when it is suspended. So half into load into the elongation. Done? Yes. So now what is load here? Its own weight. So here they did not mention it's a uniform rod of mass M or length L. So it's simply a block of mass M is suspended. So here mass is mg, load is mg, elongation is the small l. So that's why it is mgl by 2. So or half mg small l, half mg, the small l is the elongation. Don't write capital L, capital L is the original length. So option 1 is the correct one, guys. Done? Chalo. So next. So the next question. If S is the stress and Y is the Young's modulus of a material of wire, so then energy stored per unit volume. See here, so one more formula I'll write here, so related to this. So let me write. So U is equals to half into stress into strain into volume. Done? So now let me bring this volume to this side. So U upon volume is equals to half into stress into strain. Stress into strain, right? So chalo. So let's write what is energy per unit volume. Energy per unit volume is nothing but the energy density. This is called the energy density. The energy per unit volume is a energy density, guys. So in this question, see here, so what they are asking, what is the energy stored in wire per unit volume? So the energy stored in the wire per unit volume, so is equals to, I can simply write half into stress into strain, half into stress into strain. So in the question they gave, Young's modulus is given, stress is given. So we don't need strain term. So what I will do is, Young's modulus is equals to stress upon strain. Young's modulus is equals to stress upon strain. So let's eliminate this strain term. So the strain is equals to stress upon the Young's modulus. So what is stress in the given question? Yes, by, so the Young's modulus Y. So half into, so the stress value, what is the stress? Yes, into, so what is strain? S by Y. So I can write S square by 2Y. S square by 2Y. Option 4 is the correct one. So just use the logics, that's it. Done, guys? So that's it, enough for now. So the stress strain curve and the Poisson's ratio, we'll discuss it in the next session. So with the next session, we'll wind up this mechanical properties of solids. It's a small chapter. So after that, we'll start the mechanical properties of fluids. So till then, keep studying. All the very best. Bye. Take care.